We want to know the tension in the cable. I'll call that T. And all the support reactions at the square collar B. So the reactions at B. So we are told that it's a square collar at B that's going to slide without friction. That will be reflected in the free body diagram. We have a 5 kilonewton force. That will also be in our free body diagram. And we have a pulley up at E, but that will too be reflected in the free body diagram. So in the given, really everything we need to solve this is provided by the diagram and will appear in our free body diagram. So to find the tension in the cable and the reactions at B. The free body diagram step, we need to choose what is the object we're going to isolate from its connections, from its supports. So in this case, if we want to know the tension at T and the reactions at point B from the square shaft that it's on, what should our object of interest be? So the object we want, and we'll see in the free body diagram why it is a good object to pick, is the collar at B and the kind of the more thin pieces of the bar around it. So as we're going to keep that as one object, I'm supposing that thinner bar is welded solid to the collar there. So that solid piece that can go, that's the collar and that bar, is going to be the object I want to isolate. And we'll see in the free body diagram why that's going to be helpful to us. We're in 3D here. I'm going to keep the coordinate system that is provided to us, where B is at the origin. The object is going to be the collar and the thin pieces of material around it. So I have my point B here. I'm keeping the bar that goes from B to A. I have this point A. This piece that goes back to C, and then this piece that goes to D. This is my simplified object that I decided to keep, from A to B to C to D. I have, acting on the object I kept, an applied load of 5 kilonewtons. That's the only applied load. Now I have to include what are the other forces that act on my bar. Right, so what was one? Right, the tension in the rope that goes from A to E. We know that the rope starts at A and goes towards E, so I wanted to include E in my picture also. So there'll be a tension from A to E. What other force will be acting, force or forces act on the object that I decided to keep? Right. Another tension from D to E. So there's a rope pulling from D to E. What do I know about these two tensions? Right, their magnitudes are equal. I could have labeled this TAE. I can label this TDE. However, because it's the same rope going around a pulley, when we're in static equilibrium, the tension in a rope is constant even when it goes over a pulley. So actually we know that the tensions of these two forces, even though they're in different directions, their magnitudes or their value of tensions are equal. So instead of calling it TAE and TDE, I can name them both T, because I do know that their values are the same. If these two ropes met and were tied together to a point at E, because they were different ropes in that case, then I could not say that their tensions are equal. But in this case, I'm going to call them both T. It's the same value in each part of the rope. All right, so A is taken care of, D is taken care of. Now we have to worry about this support at B. Due to this, we are keeping the collar, but we are not including that square shaft as part of our picture. Because we're not including the square shaft, I have to put in my free body diagram, what did that shaft do to the collar at B? So first, we can think about translations. What translations are prevented because that shaft is there? Right, according to this, Z and X, we can't move in the XZ plane because it's connected to that square shaft. It's a shaft, though, and it's frictionless, so it can move up and down the y-axis. The shaft did not prevent that motion. So again, the motion was prevented in the XZ plane. I can model that as a force component in the X and a force component in the Z. So I'll call this BX and BZ. I'm assuming the X component's positive. I'm assuming the Z component is positive. Again, the math will tell me if those assumptions are right or wrong. This will make making the equations just a little bit easier. Right, so translations are taken care of. What rotations are prevented because that square shaft is there? Can't rotate around the X because it bangs into the square shaft. We can't rotate around Z. And because it's a square shaft, we also cannot rotate it around the y-axis. So in this case, we can't rotate it about any axis in space. So I can represent that as a moment about each of these three coordinate axes. So I can use, because we're in 3D, either a double-headed arrow, or if it's clear enough, I'm just going to use the rounded arrow. Again, I'll make the assumption that it's a positive couple around each axis. So I'm going to call this MX for the moment around the x-axis. I'm assuming it's around the positive direction. About the z-axis also, an MZ I will call it. And I'll assume positive around the y-axis and MY. Two forces, I'm modeling it as three moments, or really one moment but in three components of it. If I look at my free body diagram, I'm not quite done yet, but I have 5 unknowns at B, and I have the tension in a single rope, so I have a total of 6 unknowns. What's missing from my picture in order to get to my next step, the equation step? Right, I have no dimensions here. I need to include, or the easiest thing to include in 3D are these coordinates. B is at the origin, and the coordinates will give me enough information to be able to do cross products, enough information to find components of forces along x, y, and z. A is going to be located at 0, 0, 8. D is located at 3, 0, negative 2. These are all in meters. C, nothing happens at, so I don't need to include it. And the coordinates of E I need at 0, 6, 0. This now is our complete free body diagram for the object that we decided to keep. What's the first thing what's a good first step for finding in the equation step now? Unit vectors, we're going to need them because if we look at this tension and this tension, they're not only in x, y, or z. So thinking ahead, when we get to the force equations, we only want to include how much of each is along the x, along the y, and along the z. So I will actually prefer to start with my unit vectors here. I know that tension AE is going to be its magnitude, which we know I'm just calling T, times unit vector AE. And the tension from D to E as a vector is that same magnitude, but times a different direction. BX is only along the x-axis, Z is only along the Z, and these moments are only about an x, a y, or a z. So these are the two unit vectors I will want to find first. U hat AE and U hat DE, so I know how much of each of these tensions is along x, along y, along z. The unit vector that points from A to E, I won't go through all the details. We've seen this enough. Take the coordinates of E minus the coordinates of A and divide by the magnitude. And we get that U hat AE is 3/5 J minus 4/5 K. And for DE, we'll get negative 3/7 I plus 6/7 J plus 2/7 K. Again, I prefer starting with this step because if we jump right to summing forces, we're going to need this information anyway because we can't see how much is in the x direction without knowing the components of, in this case, TAE and TDE. Now we can use our free body diagram for the equilibrium equations. I tend to start with the force equations just out of habit. And I present them as scalars, just like I presented it for particle equilibrium. So based on the free body diagram, I want to see all the forces, or all the components of forces, that act along the x direction. Based on my free body diagram, I have all of Bx is in the x direction. None of Bz. These are moments, so they're not going to be in my force equation. The 5 kilonewton is in the y direction. So some of this tension will be in the x direction. So that is from A to E. Actually, this one does not have anything in the x direction because there's no I component here. D to E will have an x component. It has the negative 3/7 times the magnitude of DE, which I just called T. Again, the tension from A to E did not appear because it does not have an I component, but D to E does. I have one equation, but it has two unknowns in it, so I'm going to just put it aside for right now, and then come back to it once I have more information. In the y direction, there's no by term, so that's nothing to put there from at point B. I have 5 kilonewtons in the negative y direction. I have some of my tension from AE, 3/5 T, acting in the y direction. And I have 6/7 T from the force from D to E. Again, because we're going around a pulley, the magnitudes of the tensions are the same. So that simplifies this, that this is from the rope from A to E, and this is from the rope D to E. And this is all I have going on in the y direction as far as forces go. Looking at equation number 2, the only unknown I have is the tension in my cable T. So I'm going to take this opportunity to solve for the tension in the cable. Solving this, I get that the tension in the cable is a 3.43. This 5 was in kilonewtons, right, so this tension also in kilonewtons. It's positive, which it has to be because it's a tension, and I drew it in tension. I drew it pulling on my object. Now I can go back to equation 1, and I can find Bx, because I know T at this point. Bx, positive 1.47 kilonewtons. In the 3D, you don't need to necessarily draw its direction. Just as long as it agrees with your picture, that's what I'm going to be looking for. In 2D, it's easier to just draw it right or left or up or down. But here, positive means that our assumption was correct. Bx does act along the positive x-axis. Any questions so far on what we're looking at? And now we have forces in the z. We have Bz. We'll have negative 4/5 times T. And we'll have 2/7 times T. We know as a number what the value of T is, so in equation 3, our only unknown left is going to be Bz, the component of the force in the z direction. And we get that Bz is 1.76. kilonewtons. For this particular problem, we were able to solve for all, we only had 3 forces, we were able to solve for all 3 based on the force equations alone. That's not necessarily going to always be the case, because we could have some examples where we have 4 or 5 unknown forces, in which case we might be able to solve for 1, maybe 2 of them, but not all 3. So the solution step could be very different from problem to problem, what you are able to solve right away and what you have to kind of put aside and come back to. So we made 3 equations from the forces. We only had 3 of our unknowns appear in them, and we could solve for all 3. All right, force equations are done. Because I'm running out of room here, I'm going to get rid of these. We've used them. All right, what we haven't used, now that we're in rigid body equilibrium, I did all the force equations. I now need my moment equation. This is actually going to generate equation 4, 5, and 6, which I'll then split up. I want to take the moment around a point, and I know that that will be equal to the 0 vector. Looking at the free body diagram, which point does it look like is going to be the best to take the moment around? Right. B, it has bx and bz acting there, so neither of them will appear in this equation. So B seems like the more obvious choice here. All right, so we need to account for all of the things that cause a moment around point B. In 3D, I suggest actually starting with couples first and then moving to forces. It's very easy to forget to include couples in this equation, I find otherwise. So we want to find first, what are the moments caused by couples? So what should the right-hand side start to look like? What couples create a moment around point B? Right, we have 3 couples acting at B, mx, my, mz. So I can write here mx. What do I need attached to mx? It has to be multiplied by I hat. This is a vector. This has to be in component form. So it's mx, and it acts around the I hat or the x-axis. So mx introduces a moment around the x-axis. Similarly, my will have a j hat attached to it, and mz will have a k hat attached to it. It's very important not to forget the I hat or j hat or k hat here, and also don't forget the moments in general. All right, so from the 3 couples, I add that to my right-hand side. One is around I, one around j, one around k. So it's this is the magnitude of the moment, but also I need its direction. What else causes a moment around point B then, besides the couples? The 2 tensions and actually that 5 kilonewton force as well. So the forces that are not passing through point B, all of them will contribute to the moment around B. I need the moment caused by this tension around point B. Right, so it's R cross the force. So which R do we use? Right, RBD, because we're taking the moment around B. This force is located at D. Cross that with, for right now, I'll call it TDE. This will get a little bit lengthy here. We also, okay, so that takes care of the moment caused by this tension. We also have a moment caused by this tension, RBA cross TAE. Right, so moment caused by the tension acting at D, the moment caused by the tension acting at A, and because we have the applied force also, we'll have an RBA cross negative 5J. That's from the applied 5 kilonewton load. So 3 cross products here. And we have MXI, and we have MYJ, and we have MZK, all contributing to the moment around point B. Right, I can expand this out now. I just carry along these terms, the MXYZ terms. Now I need to express these cross products. So I need to write RBD, which is going to be D minus B, which will be 3, 0, negative 2, times, or crossed with, TDE. DE was this one here, so that's negative 3/7 times T, 6/7 times T, 2/7 times T. Fortunately, and this again will not always be the case, I know the value of T, so I can substitute that in here. Although in general we might not know, and then this will have variables in it. Then we have the second cross product, RBA cross TAE. That will be 0, 0, 8. And TAE is 0, 3/5 T, negative 4/5 T. And finally, RBA cross negative 5J from that applied load. I can group all of the like terms, so everything in front of I, everything in front of J, everything in front of K. So what I'll get in the end is, so all the things that have I components, I'll have a 40 plus mx minus 108 over 35t. I actually know the value of t is the 3.43. My j components, I will have my. And my k components, I'll have mz plus 18 over 7 times t. And again, I know that value. This is a vector equation. I can turn this into 3 scalar equations. I will individually set each of these coefficients equal to 0 and solve for my unknowns. So my equation 4 is going to be that 0 equals this coefficient. So 40 plus mx minus 108 over 35 times 3.43. For my equation 4, the only unknown is then mx. That'll be negative 29.4. This is in kilonewtons times meters. I get a fifth equation. I set this coefficient equal to 0. Since the only thing in that coefficient is my, it turns out that my is 0. And finally, the coefficient in front of k, I get that mz plus 18 over 7t equals 0. Solving it then for mz, mz is a negative 8.82 kilonewton meters. Between these 3 moments and then these 3 forces, I have all of my reactions.